Hi, my name is Steven Wilsons, and today we're going to have a deeper look at the spatial audio demo we showed at Build. We did a talk about spatial audio in UWP apps and games, which is a great talk to look at before you start the rest of this presentation. What is spatial audio again? So spatial audio really gives you the illusion that sounds are coming from a three-dimensional space. They will be audible all around you, and really spatial audio is sounds that are coming towards you as if they were coming towards you from real life. At Build, we're announcing that UWP developers can now convincingly use our APIs to place sound in a three-dimensional space by using Microsoft's HoloLens HRTF technology. This technology works with all headphones, all stereo headphones on the market. And you can now create spatial audio experiences in your UWP apps and games on HoloLens, desktop, phone, and Xbox One. So what are HRTFs again? Humans have just 2 ears, but you can hear sounds from different dimensions. So you can hear sounds, you can determine distance, you can determine direction, whether sounds are coming from you from above or below you. And you can hear front or back, left or right. So that's really possible because your brain, your inner ear, and your outer ear work together to make inferences about the location. We basically take sound localization cues from one ear and compare them with cues from different ears. And how that works for left or right is that sound that's coming from a certain direction will arrive sooner at one ear than it will at another. Up, down, front and back cues originate from spectral changes produced by the outer ear shape. And distance cues come from intensity and just reflection inside of a room, so basically reverb. So in conclusion, an HRTF transfers a sound to how an ear would hear it as if that sound was really coming from a real-life position. So as I mentioned, you can now enable spatial audio in UWP apps. The AudioGraph 1.0 API is the API that was available in Windows 10 and that will enhance in the upcoming release of Windows. And so the first thing to look at is, what did AudioGraph 1.0 bring us? The AudioGraph 1.0 API was a very easy API to use to build audiographs. It allowed you to take a microphone in or files in as input, and it allowed you to output to a speaker or save your output to a file. It provided functionality like low latency and effects to your sounds. The main concepts in AudioGraph 1.0 were a device input node, where you basically could connect the device like a mic and get input of sounds. Or you could create sounds from a file, and at that point you were loading the file and adding them to your graph. Each one of those nodes could have a basic audio effect applied to it, something like reverb. And you can mix all those sounds together and output them to a device, as your speakers or your headphones, or to a file. In the 1.1 API that is available at Build today, we added audio node emitters and we added a listener. So emitters really make sure that you can position sound in a point in space. So an emitter really determines where is the sound coming from. An emitter can be an input node or a submix node. The number of emitters that are supported in your application will really determine on multiple factors. Some devices are more powerful than others, and on the more powerful devices you will have more sounds that you can spatialize. An emitter can have an orientation, it can have a position in space, and it can have a velocity at which it travels. A listener is really the receiving object of audio. In AudioGraph 1.1, we only support one listener at the moment. And a listener itself can have an orientation, it can have a position, and it could also travel at a velocity. So let's look at the code we wrote and we showed you during the build talk. So the first thing we're doing in this sample is that we are creating a number of sound sources. And this sound source class here really is just a helper for me. And what it does is it creates the emitter position, which is left-right. So if you go to the left, the first parameter becomes negative. If you go to the right, it becomes positive. The second parameter here determines the vertical position in space. So up is positive, down is negative. And then the third parameter is front and back. So as I want to position my emitter more forward, I need to specify a negative value. If I want it more backwards or behind me, it becomes a positive value. Secondly, I have a file location for each of my files, for each of my different positions. So you might have guessed, I'll say front position when I load this WAV file, and front right position when I load the second one. The next parameters here are gain, which I'm really not using right now. And the last one is just the position I'm going to place my playing sound in a 2D space, just to indicate where the sound's coming from. So the next thing that's happening is that as a user starts and they click on the start button, what will happen is I want to start building my graph, which is really simple. Just this method call. And when I start building my graph, the first thing I do is I define a number of settings. I want to get some low latency, so I'm setting audio processing to raw and my audio render category to game effects so that I get the right ducking. The other things I'm doing is, as I'm creating my graph, I'm setting some encoding properties, and I'm using 48 kilohertz, which is what's required for spatial audio in AudioGraph 1.1. I'm outputting to stereo, and I'm using 32-bit encoding. So now I'm just creating my graph, and I'm checking the result to make sure that was successful. Once I've done that, I want to attach my graph to speakers, or headphones in this case. So I'll be using these headphones. So I'm attaching my device output right here. The next thing we'll do is we'll position the source in space. So I'm defining my emitter. I'm creating an omnidirectional emitter. Basically, that's what the shape is. So at this point, my sound will emit in all locations at the same time. And I'm using a very default natural decay model. I'm also setting the position of my sound, as I said. So now at this point, my emitter is created and it's positioned somewhere in front of me. Next thing I will be doing is I will be creating my file input node. And as I create my file input node, what I'm really doing here is that I'm loading the file. I have a helper function to load the file. And I'm attaching it to my emitter. So what I've done now is that I not only have an emitter, but I also have a file that plays a sound attached to it. And I will be attaching this sound to my device output. That's fairly simple. I'm also subscribing to an event that is triggered when my file's done playing. So when my file's done playing, what we'll see later is that we'll move on to the next sound. The next step we have here is creating a submix node for reverb. So we want to make sure that we have our reverb really applied separately from the sound that is going out to our device output node. So I'm specifying a 0.125 outgoing gain for my reverb to make sure it's not too loud and it sounds appropriate. I am also have a helper function specified here that creates a default reverb that is equivalent to the large room reverb that was available on X-Audio 2. And I'm adding the reverb to my submix. And now the last thing I'm doing here, or the second to last thing, is really setting the sound on my page. And then the last step is starting the graph. So now as my graph's starting, the first sound's playing. When the first sound is done playing, what happens then, the file completed event is triggered. And when the file completed event is triggered, I'm going to be updating my emitter. So I had my original emitter, and I'm going to now replace that in my graph with a new one. And that'll be the second position I want to play a sound from. So what I'm creating, again, is an emitter with the same settings as I did before, just omnidirectional and just natural decay model. Setting the position, I'm assigning a new file to it, and I'm assigning it to my device output and my submix node. The next thing I'm doing here as well, when this file is done playing, I will subscribe to the file completed event again, and once that's triggered, I will move on to the next song. And I will also remove the output nodes or the outgoing connections from the original, from the previous audio file input node we had. I will update my visual indicator on my page, and that's it. So now the way that looks, and we start running this, is that I'll put on my headphones. In order to hear spatial audio, you need to have your headphones turned on, and you need to make sure that the left and the right are correct in your head.
Front position. Front right position. Right position. Rear right position. Rear left position. Left position. Front left position. Front position. Top position. Top right position. Right position. Bottom right position. Bottom left position. Left position. Top left position. Top position.
So that was the demo. And if you had your headphones on, you'll be able to hear the spatialization of the sounds. So for the demo, the first demo we're doing, we're showing you that we have a file input node. We're attaching an emitter to it to position the sound in space. The spatialized version of the sound is directly going to the device output node. Then we're also splitting off the sound to make sure that we can apply reverb, and we're sending all of those to a submix node with a lesser gain, and we're applying reverb to it. Once we've done applying reverb to the submix node, we will send it to the device output, and you will hear it through your headphones. So the next topic I wanted to address was that the concept of HRTFs and head-oriented tracking. So with HRTF headphones, the accuracy improves greatly once you actually get to track your head, because really that's what you're doing in real life. If you're walking in a forest and you hear a bird fly over, you will move your head to try and localize the sound. And that is really what we're doing with head orientation tracking. We've learned that head orientation tracking really reduces from back confusion, so whether a sound's coming from the front or the back of you, and also helps you establish elevation better. We've noticed that head movements from 2 to 32 degrees might be required to ensure that spatial information is conveyed with very high accuracy. So for this next demo, I won't just be using the standard headphones. I'll be using the Jabra Intelligent headset, which has an IMU in it, and an IMU allows you to track your head movement. The change we're making from the first demo is that we are basically now configuring our listener object, and we'll be changing the orientation of the listener object as I'm moving my head with the headphones. So that's really the only difference from the first demo. Let's close this. So the first step is still configuring all the spatial sound sources. The second step, what we're doing really here, is that once I navigate to my page, what I will do is I will configure my intelligent headset. So I'm really querying my device to see, or my PC to see which, if any, headphones are there that are intelligent headsets. My next step is that if I navigate away from this page, I want to make sure that I clean up my resources and that I detach from the headset. All right. At this point, my page will be loaded and the user will click on the Start button. What we will do on the Start button is not only build our graph again, but we'll also calibrate the headset so that we have the correct front, after, left, right, top, bottom position. So as I said, the first step is to attach and calibrate our headset, and the second step is to build our graph. I won't actually go into detail on how to calibrate the headset because it's very specific to this headset, and it will be different to any headset you'll use. So as I'm building my graph, there really is no change with the previous step. I'm creating my audio graph. I'm setting my audio rendering category. I'm setting my encoding properties, and I'm also setting my audio processing to RAW for low latency. As I've created my graph, my next step is, again, to update my emitter when my sound has stopped playing. Again, that piece of code has not changed. Now, the next step that does change is that when I move my head, the intelligent headset will trigger an event. And once that event's changed, it basically meant I moved my headset. I moved the yaw, pitch, or roll on my headset. And I will update the listener orientation, which is the first time we'll be doing that. So what I'll be doing is I will be getting the yaw, pitch, and roll from my headset. And if I'm attached to a device output, I will convert the normal degrees I'm getting from the IMU. I will convert those to radial angles, which is what's needed for our APIs. So that's really what's happening here. I'm changing my listener orientation that way. The next step is positioning it in a quaternion. And the quaternion really, it's a four-dimensional vector that allows me to position my head, and my listener. Okay. So that's really what we're doing in this step. And the next position, the next method really is just finishing it off. As my sound keeps moving, I'll be changing my emitters. But that, again, is still the same code. So you'll see that really, all I really did was read the position of my headset or the angles that my headset's moving in, and I will be updating my listener orientation, which is really simple, but it does greatly improve the accuracy of spatial audio for users. So let's have a look at that. And while we're running the demo, what I will do is I'll pause the sound at a certain location. I will move my head, and you will notice that the sound should be coming in a position that's matched to my head movement.
Front position. Front right position. Right position.
As the sound's on the right now,
position.
and I look towards it, you'll see the sound coming
position.
from straight in front of me.
Right position. Rear right position. Rear left position. Left position. Front left position. Front position. Top position. Top right position. Right position. Bottom right position. Bottom left position. Left position. Top left position. Top position.
All right. So in summary, it's easy to use the AudioGraph to add spatial audio to your UWP apps. You can use emitters to position sound sources in space. And you can use a listener object to determine where you're hearing the audio. You've learned that head tracking will greatly increase the ability for users to localize sound. And in summary, really it's easy to enable spatial audio in your UWP apps, and we really look forward to seeing what experiences you build. As a call to action, download the code sample you saw here today from the below location. Add spatial audio to your UWP app. Have a look at Channel 9 build channel to revisit all the presentations that were given at build. And you can continue your education at the Microsoft Virtual Academy. Thanks very much for watching, and happy coding.